Okay, so I'm going to go through how to calculate empirical and molecular formulas. We're going to have a few sample problems to work through. The first question is you're given some information. A compound with the empirical formula of CH2 was found to have a molar mass of approximately 84 grams. What is the molecular formula of the compound? So in this particular type of question, you're given the empirical formula, which, as you'll note from your reading, that is the simplest form of this kind of molecular formula. The empirical just means it's reduced down where the subscripts are in simplest form. So we can generate the actual molecular formula from that empirical formula. So the molecular formula will be exactly how many atoms of each kind of element are in the actual formula for the substance. So to start out with this one, you have the empirical formula of CH2, which means the empirical formula has one carbon and two hydrogens. You can calculate your molar mass of your empirical formula by just taking your elements that are in there and going to a periodic table and getting an average atomic mass for each one. So 12.01 for carbon and 1.008 for hydrogen. One carbon, so you have 12.01 from that. And 2 times this gives you 2.016. So you can add that up and you get, roughly 14 grams per mole. You can calculate it the rest of the way out. It doesn't really matter for this part. But really what you need is pretty much, if you look at your molar mass of your molecular formula, it says 84 grams. So it's 84 grams per mole for the actual molecular formula. And the empirical formula is 14. So you can take your molecular formula mass and divide it by your empirical formula mass, which would be 84 grams per mole and 14 grams per mole, and you divide that and you get 6. So 84 divided by 14 is 6. So what you do to get your molecular formula from that empirical formula, it's this factor of 6 just multiplied through the formula, the empirical formula, CH2, and you get 6 carbons, because 6 times 1 is 6, and then your 2 times 6 is 12, and you'll have your molecular formula C6H12. So that particular problem, it asks you for the molecular formula and C6H12. The next question on here, you're also given an empirical formula, CH4O. So that's telling you the empirical formula, it's already been reduced, so that's it in its simplest form of ratios of those elements. And then you're given that the actual molecular formula's molar mass is 192 grams per mole. So if I want to look at this, I have one carbon, 4 hydrogens, and 1 oxygen in my empirical formula. Carbon's 12. You have 4 H's, so that's about 4. Oxygen is 16. You add that up and you get 32. So your empirical formula molar mass, about 32 grams per mole. And then you take your molecular formula's molar mass, which is 192. And you're going to do the same procedure as the previous problem, where you put your molecular formula's molar mass over your empirical formula's molar mass. And so you get 192 divided by 32. And when you do that division, you'll see you get 6. And then you're going to do the same thing we did in the previous part. You put a 6 in front of your empirical formula. So you're going to multiply that through by 6. And your molecular formula will be C6H24O6. Just like that. So that would be your formula, molecular formula, for that compound. Okay, on this one we have a percentage of 3 different elements given, and it wants us to determine the empirical formula for this compound. So if you're looking at your 3 elements, barium, sulfur, and oxygen, it will tell you the percentage of each one following its name, and when you have these percentages, that's accounting for 100% of the mass contributed for the compound. So if you basically assume a 100 gram sample, then those percentages could just become like grams. So if you had 100 grams of this substance, these percentages would be how many grams each one will be contributing to it. So you might just go ahead and assume that you have a sample of 100 grams so that you can work with these percentages. So your 58.8% barium, that would be 58.8 grams of barium. And then your sulfur is 13.74%. So you would say 13.74 grams of sulfur, and then you would say 27.43 grams of oxygen. So roughly, you have your, trying to see where your percentages come from. So this particular part, you can just take your 58.8 grams of barium and you can divide it by the molar mass of barium right here, 137.38. So this is how many grams of barium you have, and then you're just going to convert that to moles. So you have 137.38 grams of barium for a mole of barium. And then you're going to do the same thing for your sulfur. So you go to your sulfur, 32.07 grams of sulfur, and oxygen, 16.00 grams of oxygen and a mole of oxygen. So I'm just going to kind of bring in my calculator here so you can see, I'm going to be typing in a calculator to get me a few decimal places in there. So I'll start out with my 58.8 and divide that by the molar mass of barium. And I'll get my approximately, let's see, 0.40, I believe it was 428 moles of barium. And then I'm going to do the same thing for my sulfur, 13.74 divided by 32.07. And that's approximately 0.428 moles of sulfur. And then I'm going to do the same thing from oxygen. I have 27.43 and divide that by 16, and I get 1.71 approximately moles of oxygen. Alright, so then you convert these to the number of moles, approximate number of moles, and then you're going to divide all three of these by whichever one is the fewest number of moles. So I have two that are both the lowest, so I need to divide these by 0.428. So if I divide this by 0.428, that's 1 approximately, and then in this one the same thing is 1. Now I need to divide this one by 0.428. So, you know, if you want to use your calculator for that, you have 1.71 divided by 0.428, and then that equals 3.999 or whatever, which is approximately 4. So this tells me that my empirical formula for this sample, I'm going to take my answer for those when I divided all those by 0.428, right? So everything was divided by 0.428. You get these numbers, so then you have 1 barium, 1 sulfur, and 4 oxygens. So you would write the formula for that compound, the empirical formula would be BaSO4. Some of the questions that you may have to do when you're solving for empirical formulas may look a little like this, where you have this sample of aluminum metal and you're given a mass for it, and then you're given a total mass of the compound that's going to be produced. And it asks you to calculate the empirical formula for this aluminum chloride. So it doesn't tell you directly what how much chloride, or how much chlorine was in there, like in a direct way. So you can subtract the total mass, take the mass of aluminum and subtract it from that total mass, and so that's where your chloride part would come in. So if you know that you have 1.271 grams of aluminum in a sample of 6.280 grams total for your aluminum chloride, so this is like your total mass, and then if you take this total mass and subtract that out of it, you get like 5,000 or 5.009, sorry, 5.009 grams of Cl out of your 6.280 grams total. If you wanted to do that and calculate a percentage, well, you could do that. You could take the 1.271 and divide it by 6.280. So that looks like 1.271 divided by 6.280, and then you get, if you convert that to a percentage, you get like 20.2%. So you just would multiply that by like 100 to get percent if you wanted to. And then your remaining percentage would be from your chloride. Now if you wanted to calculate that, you could. You could do it on your calculator, or you could just say, oh, it's got to add up to 100 because percent, and there's only two things. But if you wanted to just check your math and make sure that it made sense, you could just divide that out and see what you get, and you get like 79.8. When you multiply by 100, you get 79.8%, like that. So now you have your percentages that you can use. And again, if you can assume a 100-gram sample if you wanted to, and you could say, oh, that's 20.2% of 100 is 20.2 grams of aluminum. And then your 79.8% is 79.8 grams of Cl, like that way. And then you can just see how many moles of each one of these particular ones you have by just dividing by its molar mass. So you have your molar mass for aluminum, which is 26.98 grams of aluminum in a mole of aluminum. And then off of your chlorine, you have 35.45 grams of Cl is a mole of Cl. And you see I will convert your grams of each thing into moles. So, you know, on your calculator, you would take your 20.2 for your aluminum and divide it by 27 if you want to just get close. And you'll see that that's roughly, you know, the closest thing to that is, it comes out as 0.75 on that when you do that part. And then on your chlorine, you have your 79.8 divided by 35.45. I'll do that again. 78.8 divided by 35.45. You get 2.25 roughly. So if you're trying to get these into whole numbers, you can take those and you just really divide this by the smallest number of moles. So if you divide by 0.75, because that's your smallest number, you'll see that that is 1. And then 2.25, you just take that and divide it by 0.75, and you'll see that that equals 3. So your formula would be Al, there's only one of them, and Cl3. So that's your formula, empirical formula for aluminum chloride. On some of your problems you may have this cobalt metal is mixed with excess sulfur and heated, and the sulfide is produced, and it contains 55.06% cobalt by mass. So it tells you that there's cobalt and sulfur in the compound. So that's important information to get from it. It's cobalt mixed with sulfur. The cobalt portion makes up 55.06% of the total mass of the compound. So if it's percent like this, you can just go ahead and assume your 100 grams of sample. You would have 55.06 grams of that from cobalt, and your remaining would be what, 44.94 grams from sulfur. And then convert those to moles. So go to your periodic table, and I'm going to say, okay, that's 58.93 grams of cobalt in a mole of cobalt, and sulfur is 32.07 grams of sulfur per mole of sulfur, and that cancels out there. And now you can divide your numbers. You get on your cobalt portion, you have 55.06. You divide that by 58.93, and you get 0.93, which is roughly 1. I'm going to call anything that's like 0.9, over 0.9, I'm going to just go ahead and say about 1. And then I take the 32.07 and divide it into my 44.94. about 1.4, roughly 1.5 actually. So if you take that, this number, what it was is 0.93, and you divide that into the smallest one like that. 0.93 is a smaller one, and you'll see that that still ends up being about, that's 1, and this is like 1.5. So when you go to do that, this is not a whole number, so you can't put, when you're putting your formula together, you can't put 1.5 sulfurs. So, but if you double that, you can put 3 sulfurs, right? You could do that. You could have to have a whole number. But if you double this, you have to double this. So your formula actually ends up being CO2S3. So that becomes your formula for this cobalt sulfide. So these are the ones when it gets kind of tricky. You have to get a whole number in there. So you can't leave it at 1.5 because you can't put 1.5 sulfurs. You have to have a whole number. On this one, you have percent by mass composition for these 3 different elements: copper, nitrogen, and oxygen. You're given the percentage. That from that you can go ahead and assume your 100-gram sample, and you see that your copper is contributing 33.88%. So what I would do is I would just go ahead and say 33.88 grams of copper per 100 gram of sample, and 14.94 grams of nitrogen, and then 51.18 grams from oxygen. Set it up, convert grams to moles. You're taking your copper molar mass of 63.55 grams of copper per mole of copper, and your nitrogen, straight off the periodic table, is 14.01 grams of nitrogen, and your oxygen, 16.00 grams of oxygen, like that. So you do your division. I can already tell that that one's going to come out. I'll show you on the calculator. You take your 33.88 and you divide that by 63.55, and you'll get 0.533 moles of copper. And then your nitrogen, well, you have your 14.94, and you divide that by 14.01, and you get 1.07 moles of nitrogen. And then you take your oxygen, 51.18 divided by 16, and you get 3.20 roughly moles of oxygen. And then you're going to divide all these by the smallest number of moles, which is 0.533, 0.533, and 0.533. So this particular part here, you look at your, this is going to come out to be 1, this is going to come out to be 2, and this is going to come out to be 6, roughly. So when you're looking at those, then you're looking at your formula. Copper, you have 1, nitrogen, you have 2, and oxygen, you have 6. And then later, what you'll learn is that this formula, this part right here, is actually forming an ion called nitrate, where you need 2 of those. So it actually ends up becoming this particular formula, Cu, and then we'll have our NO3, where we have 2 of those, just like that. So this ultimately will get you to your ionic compound, copper 2 nitrate. But at the very beginning, you might see it written like that, but very quickly, when you're writing compound formulas, you'll learn to make it, since it's an ionic compound, that's what makes 2 nitrate ions. Okay, so this one, you've given these percentages from this part. You're told that it has the molecular formula is what you're asked for, and the molecular formula's molar mass is 110 grams per mole. So you have to come up with an empirical formula from these percentages, and then figure out what the molecular formula is. So if you just look at your percentages again, like we've been doing, just go ahead and make it for 100 grams a sample, so that you have 65.45 grams carbon and 5.492 grams from hydrogen and 29.06 grams from oxygen. And we'll just do what we did before, convert our grams to moles using a molar mass, just from the average atomic mass on the periodic table. Okay, so we start off with this, and we'll cancel out our grams for each one, and we'll get our moles. So you have 65.45 grams of carbon divided by your 12.01, and you have about 5.45 moles of carbon, and you take your hydrogen, and you 5.492 divided by 1.008, and you'll get about the same thing, 5.45 moles of H. And you'll take your oxygen portion, 29.06 divided by 16. You get 1.82. Which is your smallest number of moles. 1.82 moles of oxygen. So you divide everything by the smallest number of moles, 1.82, and when you do that, you're going to pretty much take your 5.45 divided by 1.82, and you'll see that that equals 2.99 something, so roughly 3 and 1. And then so you look at your formula for your empirical formula, and you have C3H3O. Okay, but then if you look at this and you add up its molar mass, if you're just looking roughly at its molar mass, you have 3 carbons, and each one of those is 12, right? You have 3 carbons times 12, that's 36. You have 3 hydrogens, and each one of those is roughly 1, so that's 3. And you have 1 oxygen, then that's like 16. If you add that up, you get, let's see, 6, 9, 15, right? 3, 4, 5. You get like 55. So this molar mass is like 55 grams per mole. So the compound that you're looking for has a molar mass of 110 grams per mole. But that's not a problem if you just take your molar mass of your molecular formula, which is 110 grams per mole, and divide it by your 55 grams per mole. Then you'll see that equals 2. So to get your molecular formula, you're just going to multiply 2 times everything in there. So you end up with C6H6O2. And that compound is, that formula is your molecular formula. And then the last one from that sheet that you have this sample of calcium. It's heated in a stream of pure oxygen, and it increases its mass of the compound that it makes by 1.004 grams. And so for this one, it goes up by that much. So you have your this much calcium, and then this much is from your oxygen. So that goes into it to make a total sample. So you have 2.514 grams of calcium that's out of your total mass of, if you add those two together, you get 3.518. So that's your total mass of, the compound that's produced. And then the other part of that comes from oxygen, so you have 1.004 grams of oxygen that was from your out of your 3.518 grams total. So if you do, if you want to calculate the percentage of each one, you can just jump on your calculator and say that 2.514 divided by your total mass of 3.518, and that gives you roughly 71.5% of that is from calcium. And if you want to check your remainder, of course, if there's only calcium and oxygen in the compound, it should add up to 100, but you can check it yourself. So you can say 1.004 and divide that by your total of 3.518 and multiply that by 100, and you end up with 28.5%. Okay, so that's a percentage from calcium and from oxygen. And if you want to just assume your 100 gram sample, then that's 71.5 grams of calcium, and this is 28.5 grams of oxygen. So from here, you're just going to convert that to moles, your molar mass of calcium. And your molar mass just for an oxygen. And cross out our grams, and you have 71.5 divided by 40.08. 1.78, approximately 1.78 moles of your calcium. And then if you do your oxygen, you have 28.5 divided by 16. You'll see you get about the same thing, 1.78 moles of oxygen. And since they're the same number, you divide by 1.78. So that tells me that I have 1 calcium and 1 oxygen. So my formula, my empirical formula, which is what it asks for, is CaO, 1 of each. So that pretty much wraps up this particular sheet of practice problems that you've been provided access to. You can work these forward and backward, and just to get more and more familiar with them. That's my recommendation. Just practice them so that when you have to do it, say on a test or something, it doesn't take you very long to work through them.